Good morning again. We're going to go ahead and get started. Before we start with Chapter 4, are there any questions about kind of where the course is going? We just had our first exam. You'll notice that you don't have a grade yet because I have to go through and grade them all. And once the grades are submitted, then you'll be able to see your grade and you can kind of look back through the exam, see what you got wrong. If you want to set up an appointment with me to go over your exam, you can definitely do that. If you didn't do as well as you thought you did, you should definitely do that because we will be seeing Chapter 2 come back again. So if you were like, Chapter 2, thought I got it, guess I didn't, you'll definitely want to get that taken care of before we get to the last leg of the course, like Chapter 8. And we're almost there. We're on Chapter 4. So how's everybody doing this morning? We good? We ready to go? Talk to me. How you feeling? Sleepy, I feel you on that one. Yeah, 8 a.m. is strong. But we're going to get started. So Chapter 4 is on models of the atom. There's the YouTube video already posted, and that kind of starts with a history lesson about some of the milestones along the way to the current quantum model that we use to discuss the atom. The things that I'm not going to go over that are in the pre-recorded video are listed here. So I'm not going to give the whole history lesson. I think that's something that you can get. But I have it listed here so that you know what it is that you're responsible for, even though I don't specifically cover it here. So there's the schools of thought of Greek philosophy regarding matter, Dalton's atomic theory, and J.J. Thomson's plum pudding model of the atom. Those three things are at the very beginning of the lecture on YouTube. There's also, when we start talking about the current model of the atom, there's going to be some orbitals that we talk about. I'm not going to go over their shapes. We're going to spend more time doing electron configurations, which is where folks usually need the most help. So just keep in mind the list of things on here that you're also responsible for. When we come back next week, we'll do a couple of do now questions that'll be multiple choice, kind of like what you'll see on the exam. And I'll make sure to have a couple of questions on these topics to make sure that everybody's okay. So, with that said, are we ready to move on? So we're going to pick up with the Rutherford model of the atom. Ernest Rutherford, who was a student of J.J. Thomson, had his own lab, and he said, okay, I work with this guy, J.J. Thomson. There's this plum pudding model that he has about what the atom looks like, which is essentially that an atom is a sea of positive charge which is the pudding, and then there are electrons evenly distributed throughout. And he wanted to set up an experiment to test this idea. And if the plum pudding model of the atom was correct, then that means that you can shoot particles through an atom and they should just pass through undeflected. There shouldn't be anything in the atom massive enough to change the direction of a large particle like an alpha particle. And this is the setup. And I talked about this in the video too, but I'll talk about it here as well. So you've got a source of alpha particles, which is lead. You shoot those particles at a very thin gold foil. If the plum pudding model was correct, all of the particles would just go straight through, undeflected. And a lot of them did. But some were scattered. And some of those scattered alpha particles were scattered at really big angles. And you can detect where the particles are using this fluorescent screen. Now, you don't need to know like all the details of the experiment. This is just kind of to help you get the context. Since most of the particles pass through that thin foil, the atom is still largely empty space. But Rutherford proposed that there must be some kind of a nucleus that contains the atom's protons. He also suggested that there must be some kind of a neutral particle, because the mass of the nucleus seemed to be a lot bigger than just the protons, the positive core. So does everybody understand the Rutherford model of the atom and kind of the breakdown of the experiment? Because you will need to understand that a little bit. Just what his question was and what the results were. So talk to me about that. Okay. So this is the Rutherford model of the atom. You've got an atom that is largely empty space. At the center, you have the nucleus. And you've got that, it's made of protons and neutrons. The electrons are outside of the nucleus, and they're very, very small. So they're in that mostly empty space. That leads us to the subatomic particles. Now, you've probably heard these before: electron, proton, neutron. You are in college. You've probably taken some other science courses in high school. So this is not brand new information. But if it is, that's okay. This table summarizes everything that you need to know about electrons, protons, and neutrons. The symbols that I use, their location, whether they're inside the nucleus or outside the nucleus, and their relative charges. Electrons are negative, so we assign that a -1. Protons are positive, we assign it a +1. Neutrons are neutral, they have no charge, so their relative charge is 0. Relatively speaking, in terms of size, protons and neutrons are about the same. Electrons are super teeny tiny. So you don't need to memorize this. You don't need to know the exact ratio of their masses. Just know that protons and neutrons are the same. Electrons, super teeny tiny. We need to have some more vocabulary and some notation. So each element on the periodic table is unique because it has a different number of protons. So each element has some number of protons, and that number of protons is one of the things that gives it the particular characteristics that it has. The number of protons in the nucleus is called the atomic number, and it's abbreviated as Z. So I'm going to be using that notation throughout. So your atomic number, that's the number of protons. You'll also see it as a Z. The total number of protons and neutrons in the nucleus is the mass number. It's also A. So mass number is equal to protons plus neutrons, also represented as A. When we're representing an element, you want to write the symbol of the element, and then top left, you write the mass number, bottom left, the atomic number. So let's say that I had carbon. Carbon has six protons and 6 neutrons. If I wanted to write the atomic notation for this carbon atom, I'd write a capital C, which is carbon. What would I write for the A, the part that goes up here, the mass number? Yeah, the mass number is the number of protons plus the number of neutrons. It's going to be 12. For the atomic number, that's simply the number of protons. So that's the atomic symbol for carbon. Let's try another one. Let's say magnesium has does not have 24 protons. Magnesium has 12. 12 protons and 13 neutrons. What's my mass number for magnesium if it's got 12 protons and 13 neutrons? $25. What's my atomic number? 12. So that's all atomic notation is. Now I want to make it clear, when we're looking at a periodic table, you will always see the atomic number. That's the number that's above the symbol for the element. The mass number, however, does not appear on the periodic table. The mass number and the atomic number are always whole numbers. The only whole number on the periodic table is the atomic number, the number of protons. Neutral atoms, so atoms that do not have a charge, that means that the number of protons they have is equal to the number of electrons. Because electrons are negatively charged, protons are positively charged. If you just had 6 protons in that carbon atom and no electrons, it would have a positive 6 charge. It doesn't. The charge is neutral. So the number of protons is equal to the number of electrons in a neutral atom. In chapter 4, we're just going to talk about neutral atoms. In chapter 5, we're going to talk about atoms with a charge. Those are called ions. So just a sneak peek to chapter 5. So is everybody good on this slide? We've got atomic notation with the atomic number, the mass number, and then we're relating the number of protons to the number of electrons. Those are the major points on this slide. Let me know how we're doing. We'll do some more practice of writing the atomic notation. I just want to introduce one more bit of vocabulary. The reason why we need atomic notation is because of the existence of isotopes. An isotope is simply you have atoms of the same element that have a different number of neutrons in the nucleus. So these isotopes have the same atomic number, but different mass numbers. So let's say that I have magnesium, just like before. It's got 12 protons and 12 neutrons. Then that would be magnesium with a 24 on the top and a 12 on the bottom. If I have our example from last time, which this is, magnesium does exist as magnesium 25. Those are isotopes. Same mass number, same atomic number, but different mass numbers. Does that concept make sense? All right. Let's do some practice. So there's a table here. I want you to fill in the missing information for each row and identify the element that's being represented. So remember that an element is defined by the number of protons. So once you know the atomic number or the number of protons, you can look at a periodic table and find the identity of the element. Based on what we just talked about with how atomic number, mass number, and all these other things are related, you should be able to fill in this chart. If you haven't already, there's a periodic table posted to course content just right near the top. Grab that out. If you have a printer, print it out. If not, just have it open and work on this table. I'll give you about 5 minutes to get your periodic table, start working the things, filling in numbers. Then I'll check in with you to see if you need a little bit more time, and then I'll start helping fill it in with you. So get that periodic table and get to work. I'll check back in 5 minutes. Okay. So how are we doing? Did we get a chance to fill in the whole chart, or do we need more time? Other folks, how we doing? I know it's early. Okay. Then we can start working on this and filling it in. All right, thank you. So before I start filling this in, I'm just going to go over the relationships. So atomic number, we know that's the number of protons. Mass number is protons plus neutrons. And for the number of electrons, the number of protons is equal to the number of electrons for a neutral atom. Since we know the atomic number for the first one, we also know the number of protons. That's 9. The mass number is going to be 9 plus 10, because the number of neutrons was already provided. So that's 19. The number of electrons is going to be the same as the number of protons, which is 9. What did you figure out the element to be? I know you can't really put in the symbol, but what element is represented in this first row? Fluorine. Should be fluorine. And then when you add in the atomic notation, the mass number should be at the top, which is 19. And the atomic number at the bottom, which is 9. Now let's go through the second one. We've got our mass number already, which is 31, and we know the number of protons. With that, we can figure out the number of neutrons. You just have to subtract. So you take the mass number and subtract the protons. And the number of electrons is the same as the protons. Atomic number is the same as the number of protons. So what element did we get here? Phosphorus. And I'm doing the colors like this because that's what your textbook does. But when you're writing it for, well, you're not going to have a chapter check-in this week because you have a lot of mastering due. But when you're writing it for yourself, you don't have to do it in these colors. But if you like colors, go for it. Okay. Now we're going to do the last row. For the last row, what did we get for the mass number? It is a one-person class today. Come on, y'all. Thank you for your participation, though. Or if you got the same thing, you can just put same or, something like that. Yeah, when you put that you got the same thing or something like that, it helps me know you're still with me. And it takes the burden off of that one person. Like, well, shoot, if I don't answer, we all in this together at 8:30 in the morning. Good morning. All right. Number of protons. What do we have for that? It should be 28 because that's what the atomic number is. And the number of electrons should also be 28. What element is this? Nickel. This is nickel. You put the mass number up top and the atomic number underneath. So filling in this kind of a chart helps you know all of the relationships between all of the vocabulary words, and you're able to look at atomic notation and know what it means. So there's more practice like this. I'll be posting a chapter 4 additional practice. It's not an assignment for you to do, but if you want some extra practice, then you can work through those problems, and it'll give you a taste for the types of problems you'll see on the exam. Anybody have any questions here? Otherwise, you can let me know if you're ready to move on. Okay. The next topic we're going to cover is atomic mass. The atomic mass is the weighted average of all the known isotope masses of an element. So we were talking about magnesium with the example of what an isotope is. There's magnesium 24, magnesium 25, and magnesium 26. Those are all isotopes of magnesium that exist. But the percent abundance for all of these is different. Magnesium 24 is the most abundant. The others, not so much. A weighted average takes into account the percent abundance of each isotope. So when you're looking at a periodic table, you're going to have the symbol. Above the symbol, you'll have the atomic number. Below the symbol, you'll see some kind of decimal number. That decimal number is the atomic mass. Magnesium 24, its mass, atomic mass, is about 24 atomic mass units. And that's what we use when we're talking about atomic mass. You abbreviate that AMU, atomic mass units. So the most abundant isotope, you're going to see that the weighted average, the atomic mass, is closer to the mass of that isotope. So magnesium 24, its atomic mass is about 24, and the mass you see on the periodic table is 24.305. So it's pretty close. The other isotopes are weigh about 25 and 26 atomic mass units, respectively. Let's do an example. This is the example that I did in the video, but I want to do it again so that you can ask questions, and then we'll do a couple of practice problems together. So if you've already watched the video, that's fine. But for those of you who didn't get a chance, I want to go over this example with you. We're looking at the element gallium. It has two isotopes. And I'm going to use my highlighter here. So gallium-69 has a mass of 68.926 atomic mass units, and its abundance is 60.11%. The second isotope is gallium-71. This is the mass and the percent abundance. And we have to figure out the average atomic mass of gallium. Average atomic mass, you should read that as a weighted average. So it's not the same as just adding up the 68.926 plus the 70.925 divided by 2. That's a regular average. We have to do a weighted average, which takes into account the abundance. Before I get started trying to put together my equation for that, I like to take the information from the problem and make a table. So you have each isotope, the atomic mass of each isotope, and the masses will always be given. The percent abundance, you'll be given at least most of that information. But with the percentage, we know that the total should be 100%. So I could tell you, okay, gallium-69 has an abundance of 60.11% and leave out the gallium-71. You could still figure out what its percent abundance is and then figure out the weighted average. And we'll do a problem like that after this. So that's the information that we have so far. What I also like to do is write that percent abundance as a decimal. What you need to do to convert your percentage to a decimal is to simply divide by 100. and that will get you to your decimal. Everybody with me so far? All we did was set up a table with all the information from the problem and convert a percentage to a decimal. So let me know if you're still with me. Now we've got to take this information and calculate the weighted average, which is the atomic mass you're going to see on the periodic table. You're going to take your abundance as a decimal and multiply it by the atomic mass. That is the contribution from the gallium-69 isotope. To that, you're going to add the product of the abundance as a decimal and the mass of the gallium-71. Just so you can see where we're getting all the information from. So I want you to put that into your calculator and let me know what you get. This is really the only math that you're going to be doing in this chapter. It's calculating the atomic mass. Your calculator is going to give you and some other numbers after that. We need to figure out sig figs. The percent abundance has 4 significant figures. And our masses have 5 significant figures. So we're going to go with 4 sig figs on this one. Don't forget the units of atomic mass units, AMU. So how do we feel about that problem? You think you can try one on your own? Then let's do one. You've got element X. It occurs naturally as X6 and X7. And you've got the masses. Calculate the atomic mass, which again, read that as the weighted average, given that the natural abundance of X7 is 92.5%. I'll give you 3 minutes to set up your table and get started, and then I'll jump in and help. Alrighty, y'all. Do we need more time, or are we ready to go over it? Okay, then I'll get started. I always like to make a chart. You may get a problem that has more than just 2 isotopes, and that's when the chart really comes in handy. So if you get in the practice of doing it now, then it won't be a big deal. So in this problem, we have the atomic mass for both of the isotopes, but we've only got 1% abundance. How do we figure out the percent abundance for the other isotope? Right, you have to subtract from 100. And that completes our chart. Did anybody get an answer? Your calculator gives you that. And all the information that we were given, we've got 4 sig figs here, 3 sig figs here, 4 sig figs there. So how does that feel? Aside from there being more isotopes, This is as complicated as it gets. So if you need more practice, you're definitely going to want to go to that additional practice and work on it. You can also come to office hours today. So let's do one more. This one, you shouldn't need a calculator to do. You will see this on the exam. Exam 2 will have a question like this. It's a conceptual question. Given the only naturally occurring isotope of fluorine is F19, determine its mass from the periodic table. We said that the atomic mass is calculated as a weighted average. It takes into account the mass of each isotope and the percent abundance. We've only got one isotope. So its percent abundance is 100%. Therefore, the atomic mass that you see on the periodic table, that's going to represent the mass of this isotope. So on the periodic table that I've posted, it's got 3 decimal points or decimal places. The one in your book may only have 2. I like the one that I posted. It's got the name. It's pretty precise. But either one will be fine. So depending on what periodic table you use, you'll see this or that. But if there's only one isotope, then the atomic mass on the periodic table is the atomic mass of that isotope. Does that make sense? Sure, I can repeat that. If you have one naturally occurring isotope, that means that its abundance is 100%. It's the only thing that you have. That means that the atomic mass of the isotope is equal to the atomic mass that's on the periodic table. So that is the key. Connecting those two, that the atomic mass of the isotope is equal to the atomic mass on the periodic table. Otherwise, you're going to be looking at that problem, scratching your head like, I don't have enough information. When you do, all you need is a periodic table. So this will be on the exam. Smiley face. Trying to let y'all know so that there's no surprises. For this particular question type, yes. When you have the only one naturally occurring isotope, yes. So I could tell you if there was only one naturally occurring isotope for sulfur, which is not true, but there's only one naturally occurring isotope of sulfur, what is its, determine its mass from the periodic table. You would look at the periodic table and write down the mass that it says. Is that clear? Good. Now we're shifting gears to talk more about energy and build up our lexicon so we can intelligently speak about where the electrons are in an atom, and we can write electron configurations. So I think this is a good point to take a short break. We will take a break until 9:10. That's about 8 minutes. And if you can, during that time, get a periodic table to write on. If not, it's okay, but it'll be helpful. So break till 9:10. I'll see you in a few. All right, everybody, it is 9:10. Time to get back to it. So you may have seen a spectrum that looks like this before, particularly if you took physics in high school and you didn't sleep through it. Let's be honest. Let's just be honest. Physics, especially in high school, low key in college too. Sometimes it's not exactly riveting. Neither is chemistry sometimes, I'll be honest too. But this is something you may have seen before with talking about wavelengths and frequencies and light. This is the radiant energy spectrum. It is one long, continuous, uninterrupted band. So that means that you can have a wavelength of any length, and it'll be on this chart. You won't need to memorize specific wavelengths like, radio is this and TV is that. You'll just need to know relatively speaking. You'll also need to know short wavelengths versus long wavelengths. So short wavelengths, high energy, high frequency. Long wavelengths, low energy, and low frequency. Let's just take a second to talk about what a wavelength is and what frequency is. The distance from a peak to another peak, to the adjacent peak, I should say, or trough to trough, which is kind of the bottom of the valley, that distance is a wavelength. And that little symbol is a lambda. You'll see that for wavelength. That's the distance we're talking about. That is one cycle of a wavelength. What a frequency measures is how many of these lambdas you can fit inside of 1 second. And the more of these cycles you can do per second, the more energy the wave has. At the very top end of the energy spectrum, so this is the highest energy, shortest wavelengths, we're looking at cosmic rays. Cosmic rays come from outer space, and they're bombarding our atmosphere all the time. We've got gamma rays, which are also very high energy. Same deal. X-rays, we encounter these in the medical space. If you go to the dentist, you get, I want to say it's like once a year or like every other year, you should get dental X-rays. And then also if you've broken a bone or you think you've broken a bone, sometimes if you have issues breathing, they may use an X-ray to look at your chest. So X-rays are useful, but they're also pretty high energy. Walking down the energy line, you've got ultraviolet, so that comes from the sun. That's why you put on sunscreen. That's why you wear sunglasses, to protect against ultraviolet light. Some of that does get through our atmosphere, and it can be detrimental to the skin. Even if you have melanin in your skin, you still need sunscreen. Okay. Then there's visible light, which is the visible spectrum. It's what we see. And that's broken down by color. I learned the rainbow as Roy G. Biv. Still with me to this day. Red, orange, yellow, green, blue, indigo, violet. That is the rainbow that you see down below, just in the opposite order, because we are going from the highest frequency to the lowest frequency. So it's violet, indigo, blue, green, yellow, orange, red. You'll need to know this relative order, because when we talk about comparing energy or frequency or the length of the wavelength, you'll need to know, which color of visible light is longest and shortest, etc. Then you've got infrared, microwaves, TV, and radio. So know all of these, know the relative order, short wavelength, long wavelength, energy, so forth. Does that make sense to everybody? Okay. You're switching it up this time. So let's do some practice just to make sure. We're going to consider blue light and yellow light. Of those two, which one has a longer wavelength? Blue light or yellow light? And I've got the reference down at the bottom. You can put your answer in the chat. Longer wavelength. Blue or yellow? If you feel like it's the same, you can put the same, or you can put your answer. If you think it's yellow, you put yellow. The longer wavelength is going to be yellow. So remember that this chart is oriented with high energy on the left and low energy on the right. High energy means a short wavelength. Low energy means long. So we're looking for the one that's closest to the right-hand side, and that would be yellow. Now, which one has a higher energy, blue or yellow? You could just put B or Y. Blue. So that's the one closest to the high energy side. The shorter wavelength, higher energy. Which one has a higher frequency, blue or yellow? Blue. Because with the short wavelength, you've got high energy and high frequency. Frequency is a little fancy F, the little tail on it. Now let's consider infrared and X-rays. We're going to answer the same set of questions. Which one has a longer wavelength, infrared light or X-rays? You just put I or X. I agree. Higher energy? I or X? The X-rays are going to have higher energy. Shorter wavelength means higher energy. And a higher frequency is also going to be X-rays. So make sure in your head you know short wavelength, high energy, high frequency. Long wavelength, low energy, low frequency. If you know one, then you know the opposite is true for the other. So you don't have to memorize both, just know one of them. So how we feel about these practice problems? Because you'll see something like this on the exam as well. Okay. So moving right along. We talked about the Rutherford model of the atom, which is pretty, in terms of the structure, pretty good. Protons and neutrons in the nucleus, electrons in the empty space around it. Great. But there's some more detail here. Niels Bohr speculated that electrons orbit around the nucleus in fixed energy levels, and that these electrons are only found in specific energy levels and nowhere else. That concept is called quantized, okay? We've got quantized energy levels. So if this is energy level 1, and this is energy level 2, you're not going to have any electrons in between. You're either in n equals 1 or n equals 2, not in between. That's the quantum concept. I think the analogy I use in the video is steps. You can't walk down half a stair. You're either on step 1 or you're on step 2. There is no in between. Make sure you understand that concept of quantization, that you have electrons in specific energy levels and nowhere in between. We're going to build on that concept. So if it doesn't make sense by the end of the next couple of slides, I'll check in and make sure we're all good. So part of the evidence that was used to show that electrons only exist in these in discrete energy levels is emission line spectra. So if you have an element in a lamp and you heat it up really, really hot so that it's a gas, and then the particles get excited, they release light. That light is filtered through a slit, and then a prism is used to separate the light into the different colors. What you see is very distinct bands of light. Each element has its own unique emission line spectrum. So when those electrons get excited and then they drop back down to their ground state and release energy, you see specific lines for specific elements. Remember that the color spectrum is continuous, but we don't see that here. We see distinct bands of light. So this is evidence that electrons only deal in certain amounts of energy. When electrons move from one energy level to another, they're either going to absorb energy or release energy. So let's say that you have an electron, we'll call this level 1, and we want to get to level 2. You have to put in a certain amount of energy. If you don't have at least that amount of energy, you can't get up to that next level. So if you think about going up the stairs, if a stair has a certain height, you need to lift your foot up at least that amount to get onto the stair. Otherwise, you're kicking the stair. That doesn't work. Once you get up to level 2 and you want to go back down to level 1, you're going to release a photon. A photon is just a particle of light. And what's released, that's what you see in the emission spectra. So let me know if you're still with me. We talked about a few things that I'll summarize. Electrons exist in energy levels. They're not exactly fixed like Niels Bohr suggested, because electrons can move from one energy level to another. But we know that energy levels exist because of emission line spectra. When an electron absorbs energy, it has to absorb a certain amount to move from one energy level to another. When it falls back down to a less excited state, it releases a photon. That photon, that particle of light, is what you see in an emission spectrum. So that's the summary. Is everybody still with me? Do we need to explain something again? Let me know how we're doing. I'm going to take a swig of tea because my throat has been sad. So y'all think about life. I'm going to take a swig of tea. Yes. So you release light when you're dropping back down, when you're going from an excited state to ground state. And there's one more concept that we need to talk about on this slide. You may see this on your homework. I'm not going to be too concerned with it on the exam. But the idea is that, let's say that I had these two energy levels. and I had 1,000 electrons at n equals 1, and I need to get them all up to n equals 2, then that means that I need 1,000 times the energy that it would take for one electron to be excited. Let's say I get them all up to energy level n equals 2. And they drop back down to n equals 1. That means I'm going to release 1,000 photons of light. Each electron will absorb or emit a photon when they're going up or when they're coming back down. So one photon is associated with each electron. They each need their little bit of energy to go from n equals 1 to n equals 2. And they will all release that energy to go from n equals 2 back down to n equals 1. Does that concept make sense? So it doesn't matter how many electrons you have, it's going to be that many photons that you need. Okay? We're about to dig into energy levels and sublevels. This is a very abstract part of this chapter. It may take a little bit of practice and kind of talking it through for it to make sense. We're talking about something that we literally cannot see. So sometimes that's a little bit difficult. If it makes sense in class and then you go back to your notes and you're like, wait, what? It's really okay. Make sure you watch the YouTube video. Make sure you do practice problems and utilize office hours. If office hours for today don't work, then as soon as possible, make an appointment with me so we can go over the concepts you're missing, or we can talk about the homework problems that you don't understand. We're talking about the energy levels. These are the energy levels that Niels Bohr speculated that we know they exist. These energy levels, you'll also see them called principal quantum numbers. You'll also see it referred to as N. N can have a value of 1 to 7. These energy levels, you can think about them as the floors in a mall or a parking deck. If you're on level 1, it doesn't take a whole lot of energy to get there. And let's say that the elevator is out, right? So if you park on the first floor, you're lucky. You just walk right in. But if you park on the 7th floor, it takes a whole lot more energy to get up there to your vehicle. You might be kind of mad, especially if it's hot. Car smell and it's hot, trying to walk up 7 flights of stairs, it'd be a struggle. Each of these energy levels can be broken down into sub-levels. In those really big parking decks, you might see so it may be level 1, but it may be 1A and 1B. Right? It's got this side and this side, or the slightly raised side. That's exactly what it is with these sub-levels. You have the big energy level, like n equals 1. And then you have a sub-level, which can be S, P, D, or F. Those are the sublevels. I'm going to write out what each of these has. For n equals 1, you only have the S. So this is the energy level. These are the sublevels within that big energy level. N equals 2. We have S and we have P. N equals 3. We have S, P, and D. N equals 4. We've got S, P, D, and we have F. We're going to stop there because it's pretty much more the same. Okay. But this just gives you the idea. Each of these big energy levels can be broken up into sublevels. N equals 1 is the only one that has just one sublevel. So if you're in N equals 1, you're in the 1s. The s orbitals are shaped like spheres, so that's why it's drawn like a circle. We're not going to go over the different shapes, but that is in the YouTube video, and that's it's important, but not as important. Does everyone get the concept of the energy level versus the sublevel? Because that's the major thing here. Let me know how we're doing on that. Okay. So we've got energy levels, we've got sublevels, now we're adding on orbitals. An orbital is a region of space where you have a high probability of finding an electron. So to break down what that means in terms of the other terminology, energy level, sublevel, orbital. So if the energy level is which floor you're on in the parking deck, and the sublevel is like 1A versus 1B if it's like one of those really big ones, the orbital, that's like your parking space. Okay? You are very likely to find your vehicle in the space you parked it in. If not, you've got some big issues. I hope you have AAA. But in terms of size, we're going smaller and smaller. Energy level is the big energy level. Sublevel, we're chopping it down some. Orbital, we're chopping it down more. So we talked about n equals 1 and 1s. The orbital, there's an s orbital. And there's only one of them. In n equals 2, we've got the 2s and we've got the 2p for sublevels. There's always just one s orbital associated with each energy level. But there are 3 p orbitals in the 2p sublevel. So if we total up the orbitals for each level, n equals 1 has 1 orbital. N equals 2 has the 1 orbital in the s plus the 3 orbitals in the p for a total of 4 orbitals. So there's 4 different locations that are high probability for finding electrons. Let me know if that concept makes sense. We just added on orbitals. And if it doesn't make sense or you need me to repeat something, let me know. Okay. One more thing on orbitals. The higher the energy of the orbital, the larger its size. So if we have n equals 1, and let's say that's the 1s, then n equals 2, if we're looking at the 2s, will be bigger. Another way to say this is that the electrons are farther from the nucleus. So the larger the size of the orbital, the higher the n, the energy level, then the more electrons you have that are going to be far away from the nucleus. Because remember, the nucleus is in the center. So if you increase the n, then that means you increase the distance between electrons and the nucleus. That concept will come back around in chapter 5 when we're talking about periodic trends. So hang on to it for now, and it'll come back again. So make sure this is in your notebook. Are we ready to move on from this slide? I know you probably have another couple things to write down, but let me know when you're ready. Now we're building up to write electron configurations and draw orbital diagrams. Let's talk about these energy levels and how many electrons they can hold. Each orbital can hold a maximum of 2 electrons. So in energy level 1, we've only got the s sublevel, the 1s. There's 1 orbital there. If we're trying to figure out how many electrons it can hold, we've got 1 orbital times 2 electrons, and that gives us a total of 2 electrons for n equals 1. Energy level 2, we've got the 2s and the 2p. That's 2 energy sublevels. S, we only have 1 orbital. So we've got 2 electrons there. In the 2p sublevel, we have 3 orbitals. and each of those can hold 2 electrons. So the 2p sublevel can hold 6 electrons. For energy level n equals 2, you can hold 8 electrons in there. But what about the total number of electrons? If I have electrons filling just the 1s, that's 2. But if I have it filling both the energy levels of 1 and 2, so I've got 1s, 2s, and 2p all full of electrons, then that means I have 10 electrons total. So an element that has 1s, 2s, and 2p all filled has a total of 10 electrons. Let's do the energy level equals 3. S only has 1 orbital, so 1 orbital times 2 electrons gives us 2. The p sublevel has 3 orbitals, and each of them can hold 2 electrons. Now we've got the d. The d sublevel has 5 orbitals. And if they each can hold 2 electrons, we get 10 electrons in the d. So I'm going to write for you, which this is in the lecture that's already online, but I just wanted to be clear here too. The s sublevel, you've got 1 orbital. The p sublevel, there are 3 orbitals. The d sublevel, there are 5. In the f, you have 7 orbitals. If I had an element that had n equals 1, n equals 2, and n equals 3 filled, then the total number of electrons that I would have, I'd have to add on another 18 electrons. So 18 plus 10 gives us 28 electrons total. Does this make sense to you in terms of counting how many electrons in each energy level? So if I had an element that had energy levels 1, 2, 3, and 4 completely filled, how many electrons would that be total? What would I be filling in here? Yes. That element would have 60 electrons. Let's move on to electron configurations, because that's what we've been doing. We've been talking about where the electrons are in an atom. We can use the periodic table to write electron configurations. If you have a printed copy or you have a tablet or something where you can kind of draw and write, get that periodic table. We're going to identify the different blocks on the periodic table in terms of which sublevels are being filled. If you have color pencils, this is a good time. And if you want to do it after, that's fine too. So everything in black is the S block. That means that it's filling an S orbital. We've got 1s, 2s, 3s, 4s, 5, 6, and 7. The energy levels that we were talking about, n equals 1, 2, 3, 4, 5, 6, and 7, like that. That's the main energy level. It's called a period. We're going to talk more about that probably in chapter 5. But each row has a number. The next block that fills is the P block. That means that all of these elements here are filling a p orbital. The next one is the D block. Oh, before I get ahead of myself, I didn't number the P's. So we've got 2p, 3, 4, 5, 6, and 7 for the P's. The elements in the D block are filling a d orbital. Starting with 3d, which I know it's in the 4th row, but energy-wise, the 3d is slightly higher in energy than 4s. So that's why it gets filled later. The last block is the F block. Notice that there's an asterisk and then 2 asterisks here. What that means is this table goes up there, but it is traditionally drawn underneath, just so that you maintain the blocks. Otherwise it would throw off the D block and the P block. It would look a mess. This is the F block. And you're filling an F orbital here. There's 4F and 5F. If you have this periodic table labeled like this, it will help you tremendously in writing what's called the full electron configuration, which simply tells you where all of the electrons are in a neutral atom. The order that all of these orbitals fill is literally what you're reading off of the table. The first thing that fills is the 1s. After that, you don't have anything else in the first row, so you move down to the second row. The next thing you see is the 2s. After that, it's the 2p. Everything is filled there, so I drop down to the third row and I fill the 3s. Then I fill the 3p. If I drop down to the fourth row, so now we're here, what do I fill first? The 4s. What comes after that? Nope. You're literally reading across the table. Yeah. So the 3d is next. Then the 4p. So you're reading each block. And that's the order that the electrons are filling these orbitals. So after the 4p, there's the 5s, 4d, 5p. Drop down to n equals 6. You've got 6s, then 4f. So remember, you see that asterisk? You go down to this table here below. Then you come back up for the 5d and the 6p. You do the same pattern in row 7. You've got 7s, 5f, 6d, 7p. That's the order that the electrons will fill. So if you know this order, you're good to go. This is your cheat sheet for chapter 4 when it comes to writing electron configurations and understanding how to write orbital diagrams, which we're going to cover in just a minute. If you do not have this right now, make one or print this one off in color, something like that. But you will need something like this to study with and to do your homework. Believe me, it makes your life easier. If you're not usually the type to go through the trouble of having different colors, you're going to want to do it this time. So I'm going to move on from this slide. If you need to reference it, it will be posted in the lecture notes. Let's do some practice writing configurations. Write the electron configuration for a neutral atom of zinc. This is the first of 2 problems that I put forward in the video online that's already online. And I said try it yourself if you want to. We'll go over these in class. The first thing you want to do is find the element that you care about. We're looking at zinc. Zinc has 30 electrons. I'm going to quickly label so that you can see. Now we can write an electron configuration. We know the order, but we need to include the number of electrons in each. So this is telling you the maximum number of electrons that can be held in each sublevel. We're not going to worry about the F because we don't need F. When you're writing an electron configuration, you always start here. Start with 1s. And you're going to fill each of these sublevels until you get to the sublevel that your element is in. So that means for zinc, it's in the D block. It's in 3D. So everything that comes before 3D, we know is completely filled. So if I have the 1s sublevel, I know it contains the maximum number of electrons, which is 2. So I'm going to write a superscript 2 after the S. And that tells me the number of electrons. After we fill the 1s, we go down to the n equals 2, so the second row. We're going to fill the 2s, and it can hold 2 electrons. Let's keep up a tally. So right now we've got 2 plus 2. That gives us 4. We said zinc has 30. So we've still got a ways to go. We filled the 2s. Now we fill the 2p. The 2p can hold a maximum of 6 electrons. So we write our superscript with a 6. Now we're at 10 total electrons. We've still got 20 more electrons to place. Now we're in n equals 3. We fill the 3s with 2 electrons. That gives us 12. We go over to the 3p. Now we're at 18. We drop down to energy level 4. We fill the 4s completely. That's another 2. Now we're in 3D, and here we should count. So once you get to the block that your element is in, you want to count off how many spaces. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Zinc is at the end of the D block, so that means it is completely full. the sum of all these superscripts, the little numbers, that should equal the number of electrons in your element. And remember, on the periodic table, you have the atomic number. The atomic number tells you the number of protons, which is equal to the number of electrons in a neutral atom. Talk to me about this process. How do we feel about writing an electron configuration? Do you think, given this chart, you could write one yourself, or do we need to talk through another example? Okay. Then I've got one more example, which is a long one, okay? We need to write the electron configuration for neodymium, which is all the way down here. You can go ahead. I'm going to continue labeling this periodic table. In your notes, I want you to try to write out the configuration for neodymium. So I've put here all of the labels. This is going to be a long one, but we're going to walk all the way across the periodic table row by row until we get to neodymium. It has 60 electrons. We know that because it's a neutral atom, and we know the number of protons is 60. Always start with 1s. We fill that completely. We drop down to the second row, fill the 2s and the 2p. Now we are at the third row. We fill the s and we fill the p. Fourth row, we fill the 4s, then the 3d, then the 4p. Fifth row, 5s, we fill that with 2, 4d we fill with 10, 5p we fill with 6. We're getting close. Now we're in row 6. We fill that 6s2. Then we go to the 4f. And we count 1, 2, 3, 4. This should total 60. So you go through, you add it up. But this is the electron configuration for neodymium. In chapter 5, we're going to learn the abbreviated configuration, which is a lot less time consuming in terms of writing, but you have to understand the full electron configuration first before we can bring on the abbreviations. So talk to me. How do we feel about it? Better than before? Okay? Still good? Then here's what I want you to do. I want you to write the configuration for a neutral atom of iron. I'll give you a couple of minutes to do it. I'm not going to label the periodic table yet. I'll give you 2 minutes to get started, and then I'll label. Just to help you out a little bit, there's iron. 2 minutes, and then I'll check back. I'll start labeling the periodic table, and then I'll write it out. I'm not going to label the whole thing because we don't need the whole thing. We just walk it across the periodic table. We're looking for a total of 26 electrons, starting with the 1s. We fill that completely. We drop down to row 2, which is n equals 2. We completely fill the 2s with 2 electrons. Walk on over to the p block and fill the 2p. So far, we've got 10 electrons. We're looking for 26. We're not even in the same period as iron yet. Period 3, we fill the 3s, fill the 3p. Now we're at 18. Period 4, fill the 4s, and now we're in the D block. This is where iron lives. So we're going to count these. 1, 2, 3, 4, 5, 6. 18, we added another 8. So that gives us a total of 26 electrons, which is what we're looking for. So let me know how you did. Did you get it? If you didn't write it down because you're like, I don't need to write that down. Is this what you thought it should be? Let me know. One more practice for you. Instead of writing the configuration, I want you to identify the element that has this configuration. 1s2, 2s2, 2p5. I'll give you 2 minutes. Wrestle with your periodic table, and then I'll check in. So let's look at this one. We have an electron configuration, and we have to identify which element it is. One s2 means that we have gone through the n equals 1. So it's not hydrogen, it's not helium. We can check those off. We've got more electrons than that. 2s, there's that. 2p5, 1, 2, 3, 4, 5. So it should be fluorine. The other way you could have done this was to total up the number of electrons. 2 plus 2 plus 5 gives you 9 electrons. And in a neutral atom, that means 9 protons. And you look for the element that has 9 for its atomic number. Questions on this one? Well, that's all I have for you. That is the majority of Chapter 4. You do need to watch the video that's already on YouTube. This video will also be posted as usual, along with the notes. Some things to remember. You've got Mastering Chemistry for Chapters 3 and 4 due on Sunday. That's the 28th. So hopefully you started Chapter 3 last week so that you don't have to do 2 chapters on Sunday starting at 8 o'clock p.m. Exam 2 will cover Chapters 3 and 4, and it will be available on March 3rd. So next week, we'll do exam review, and the exam will be available the day after class. Office hours are going to be from 11:30 to 1 p.m. I'm just going to make that change because 11 o'clock is just a little bit too much of a scramble. So 11:30 to 1 p.m., that's my office hours. If you have questions, you just want to say hi, you want to have some study tips, come on by. If you have questions for me, this is a good time. Otherwise, you're free to go.